Stanford University.
Yeah, we're going to come back to the supersymmetry business. Boy, this is very abstract stuff, and I really am surprised that anybody returned after the last time. But we're gonna keep going, and we'll see we'll see who gives up first. Okay. Yeah.
I asked about the Casimir effect last time as driving evidence.
Does everybody know what the Casimir effect is? Well, it's an effect of quantum field theory. It can be described in a number of ways, but it's just if you take two reflecting surfaces and hold them a certain distance apart, then there are effects of quantum field theory. Roughly speaking, you can say that, well, let's not have the conducting plates there. Then there's a vacuum energy, and the vacuum energy can be thought of as coming from virtual production of pairs of particles in the vacuum. That's one way to think about it. You can also think of it as the 0-point energy of oscillators, harmonic oscillators that are associated with the quantum fields. Same thing. And in empty space, purely empty space, there's a certain amount of energy that's present as a consequence of these virtual processes. Now, the virtual processes also take place in the presence of these conducting plates, but the conducting plates kind of interrupt these processes. For example, roughly speaking, virtual loops, which would have been present in the vicinity of these plates, had the plates not been present, are going to get affected by these reflecting plates. For example, if this is a reflecting pair of plates and the loop here are photons, the photons, roughly speaking, will reflect off the plates. So the virtual processes will be kind of interrupted by the presence of these plates in ways that would not have been there if the plates had not been there. That's all. There is an effect of the plates on the virtual processes. The virtual photons in the vacuum get reflected off the reflecting surfaces and so forth, and that modifies the value of the energy density, the vacuum energy density between the plates. Also somewhat on the outsides of the plates. If you take the plates far apart, very, very far apart, then it's true that each plate by itself still does some interrupting of the vacuum diagrams and modifies the energy, but it modifies the energy in a way which depends on the distance between the plates. Far away you get one answer. As you bring them together, more complicated things can happen. Photons can bounce back, virtual photons can bounce back and forth between them, and the result is that the vacuum energy, or the 0-point energy, becomes a function of the distance between the reflecting plates. When energy is a function of distance, that is an indication that there's a force. You can think of the energy as a function of the distance between the plates, and you can think of it as potential energy. The derivative of that potential energy with respect to distance is a form of force. So there's a quantum field theoretic origin of force between reflecting plates, which disappears rather rapidly as you separate the plates. I think it goes as 1 over the distance to the 6th power, if I remember. 4th power? 4th power. So much faster than the force goes as a 4th power, or the energy?
The force.
I can't remember. Yeah, you can work it out just on dimensional grounds, in fact, but I won't do that right now. And that creates a force between the plates which is typically attractive. So that's a detail that you have to work out. The force is attractive. In fact, if these were fermion loops here, the force would probably have the opposite sign, I think. So this is and this force can be measured. It actually is measured. It's difficult to measure. It's a very small force, and it falls off rapidly with separation. But it's often taken to be a confirmation of the idea of vacuum energy. It is to some extent, but on the other hand, you can also just think of it as a force between the plates when they get close together. Anyway, you asked me about the Casimir effect.
The question is, what other confirmation is there of the vacuum energy? Because that is such a small effect, it seems a little weak.
Well, there's all kinds of processes and detailed, high-precision behaviors of atoms and so forth, atomic spectra and so forth, which are sensitive to these vacuum loops. Yeah, so they're indirect measurements. The direct measurement, what do you really mean by vacuum energy? What do you really mean by energy? Energy is mass, E equals mc squared. Mass is the source of gravity. The basic thing that mass and energy do at a very fundamental level is that they gravitate. Okay? So the question is, would this energy that's stored between these two plates here modify both the mass of these plates, and would it affect the gravitation of some other object out here? And that, of course, is much too hard to measure. That's way, way beyond the ability to measure. But the vacuum energy that's present just in empty space gravitates, and the effect of that gravitation is the accelerated expansion of the universe. So really, when people talk about vacuum energy and real honest evidence for it, the only real evidence for it is the accelerated expansion of the universe. So that's, I would put it that way. There's other ways to think about the force between these plates here than thinking about vacuum energy. You can just think about it as the force between plates. Yeah.
How can the Casimir force ever be positive?
You know, how can they be repulsive? You know, how can they... I think it depends on the kind of particle that's... I believe that if there were fermions which were mediating the force, that it would be positive and not negative. I think that's true. I have to check that, but I think so.
Do you have any idea why the popular articles about vacuum energy all call it mysterious and seem to say it's it's an unknown? Do physicists?
Look, I've explained this over and over again. All quantum field theories predict the existence of vacuum energy. Is that mysterious? Well, okay, it's something that's very, very well established in quantum field theory, that there is a zero-point energy for every quantum field. It's called vacuum energy. It's really there. Here's a measurement of it. In that sense, it's not mysterious. It's a mathematical consequence of quantum field theory. The really mysterious thing is not that there is vacuum energy or dark energy or whatever you want to call it. The really mysterious thing is that there's so little of it. That's the really mysterious thing. Why is there so little of it?
I understand that. But then they say this mysterious thing about vacuum energy, like nobody knows what it is.
What can I do?
I just want to be reassured that that's the right response to that, to those sentences when I read them.
Right.
That I wasn't missing.
No, as I say, the mysterious thing is its absence, not its presence. Okay, look, because it is such a feeble thing, because it is so so small, for many, many years, physicists, including Einstein, thought it must be exactly zero. They convinced themselves that there must be an explanation of the fact that it's exactly zero. There was no argument. There was never an argument about why there shouldn't be vacuum energy that gravitates. But since it seemed to be absent, it seemed to be absent to rather high precision, the psychology was, well, it must really not be there at all, since it's so much smaller than is expected on the basis of just quantum field theory plus a little bit of dimensional analysis. Since it's hundreds of orders of magnitude smaller than what you would expect, there must be some principle of physics which says that it's not there. The right theory of nature, as we all know, is string theory. Therefore, there must be a principle of string theory which says that there is no vacuum energy, and that must be the explanation. Now that we have an explanation, it is an extremely mysterious fact that when the next round of experiments were done to probe the existence of vacuum energy a little more precisely, it turned out that it was there. All right, so it was entirely a psychological mysteriousness. We convinced ourselves that there must be an explanation of its absence. And then when it wasn't absent, everybody said, wow, oh my goodness, that's mysterious. Well, it is mysterious, but what's mysterious is the fact that it's so absent. So, but what it is, it's surely some form of vacuum energy that, yeah.
So I have a supersymmetry question.
Yeah.
So these bosons, I can have a large population of them in the same state.
Uh-huh.
So suppose I have, in our small example, a set of bosons in the same state,
Right.
and I apply the symmetry transform. Now I've got a bunch of fermions.
No. 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 What the symmetry, okay. It's exactly this fact. All right, the symmetry transformation is generated by or induced by these operators Q, okay? They're analogous to some extent like other generators, other symmetry generators, let's say angular momentum. But there's one thing, what do? An angular momentum generator just rotates by an infinitesimal angle. What a supersymmetry generator does is it doesn't turn a system of bosons into a system of fermions. It removes one boson and replaces it by one fermion. So if I had 1,000 bosons, the supersymmetry operation, the supergenerator, the generator of the symmetry, would take one boson and replace it by a fermion, or one fermion and replace it by a boson. It wouldn't take all of the fermions and replace them by all of bosons or vice versa. Now, you say, wait, but why can't I act multiple times with this Q and take large numbers of fermions and replace them by bosons? The answer is that Q squared is equal to 0. That's the character of these fermionic, of these Grassmannian variables, that they have the property that when you act twice with them, you just get nothing. So compare it with the generators of rotation. You make a small rotation of space, and that changes everything a little bit. But then you can compound that rotation many times by rotating a little bit, rotating a little bit, rotating a little bit, rotating a little bit, and turn everything around. Okay? You can't do that with these fermionic generators. You operate with Q, you replace a fermion by a boson. You operate again with Q, and you get nothing. So the way to think about it is what Q does is not to replace all fermions by bosons, but to remove one fermion and replace it by a boson, or vice versa. So it changes you by 1 unit of fermion number.
As far as the motivation for supersymmetry, is there motivation other than getting rid of the vacuum energy?
A little bit, yeah. All right, so let's talk about that now. There are 3 things that supersymmetry does for you, all of which sound quite significant and may be quite important, or they might just not be. And the answer is, at the moment, we don't know. By supersymmetry, I mean supersymmetry measurable within the next decade at the machines that are now being built, LHC in particular. The first thing they do for you is to control these enormously big numbers which occur and which force you into thinking about extreme fine-tunings of variables, in particular the Higgs mass itself. The Higgs mass, as we've talked about, would naturally, if there was no funny thing going on, would naturally get shifted up to some very large mass. Excuse me. And the only way to control that is either, yes, I agree, is either by extreme fine-tuning of the parameters or by the symmetry which replaces fermions and by bosons. So that's the first fact, that it controls the, let's just call them divergent self-mass of the Higgs, and prevents the entire remember, all of the masses of the particles are responses to this Higgs phenomena. And if the Higgs particle got dragged up to some very, very high energy by these divergent Feynman diagrams, everything would get pulled with it. And all of the masses of all the ordinary particles would be way, way up at some enormously high energy, presumably something like the Planck scale. So that's the first thing. It creates the cancellations which control this. All right? We've talked about that. Second thing, it gives you candidates for stable particles which may be stable new particles. It gives you candidates for new kinds of particles which could play various roles in physics, in particular dark matter. Dark matter is not dark energy. Dark matter is believed to be particles, and it's believed to be particles which have not been detected yet. Saying they've not been detected yet probably means they're very heavy, at least by the scale of current experiments. Supersymmetric particles, when they decay, will always decay. There are particles, the ordinary particles, and there are their partners. Particles and partners. If an ordinary particle is a fermion, its partner is a boson. If an ordinary particle is a boson, then its partner is a fermion. So you actually separate the world into 2 kinds of particles, those which you ordinarily think of and those which are their superpartners. Right? Now, whenever a superpartner decays, here's a superpartner. It's an eno of some sort, a Higgs eno or an eno. A Higgs eno or a glue eno or a photino, one of the supersymmetric particles which have not been detected yet. Whenever it decays, it gives off an ordinary particle plus another supersymmetric partner. Supersymmetric partners don't go away. That means there's always going to be, if you start with a partner, you'll wind up with a partner. You can't get rid of them. You can't get rid of them. There's always one of minimum energy which is stable. The one of minimum energy which is stable is usually called the LSP, the lightest superpartner, and it can't decay easily. It can't decay, well, in principle perhaps it can decay, but that's another story, supergravity, all sorts of complexity. But the simple story is that the lightest superpartner will not decay. Now, whatever dark matter particles are, they're believed to be rather heavy, maybe a TeV, something like that. Why don't they decay to ordinary particles? Something must prevent them from decaying to ordinary particles. How do we know they don't decay? Because they've been around for about 10 billion years. That's how we know. That doesn't mean they'll never decay, but it sure means that they don't decay at the rate that you might have expected from ordinary particle physics. They seem to be exceedingly stable. And so supersymmetry provides you with another class of particles, the lightest of which is likely to be stable. From experiment, we know and we expect that the lightest of the superpartners will weigh something like about 1 TeV, and so it provides a candidate for dark matter. Whether it's the right candidate or not, we don't know. And the rough orders of magnitude of the masses of these particles, their properties and so forth, seem to be good, respectable candidates for dark matter. So that's the second fact. Another way to say it is, look, we already know that there are particles that have not yet been discovered in nature. By discovered, I mean discovered in the laboratory, or even discovered in cosmic rays or anything like that. The graviton is one of them, but that's, we're not thinking about that. There's the dark matter particles. So whatever the dark matter particles are, they do require another, we use the word sector, another sector of particle physics. They're very weakly coupled to our kind of matter, we know that. Otherwise, if they were strongly coupled, what would happen if when they banged into a nucleus, they would be slowed down or let's suppose they were electrically charged. Electrically charged and not tremendously heavy. What would happen to them, to the dark matter in the galaxy? The answer is it would scatter off the ordinary matter. And in scattering off the ordinary matter, the enormously large halo, which is much bigger than the galaxy, the large halo of dark matter, would get scattered. And when it gets scattered, it would lose energy and fall in and basically coincide and be at the same place as the ordinary matter. So whatever it is, this dark matter, it whizzes back and forth through the ordinary matter, through the plane of the galaxy, through all ordinary stuff without interacting with it much. Supersymmetry provides good candidates for this kind of thing. So that's another reason not to believe it, but to think this is an interesting direction to explore. And the last reason is extremely interesting. We've talked about it a little bit. We've talked about renormalization of coupling constants. I told you, for example, that electric charge of an electron at small distances is larger than the electric charge at large distances. This is this phenomenon of screening. It's also the phenomenon of renormalization. Renormalization changes the input parameters to the output parameters. The input parameters generally govern physics at very small distances, or equivalently very high energy, and the output parameters govern physics at lower, more accessible energies, and they're not the same. So in particular, there are the coupling constants such as the electric charge, the fine structure constant, which is just a square of the electric charge of the electron in some units. It's a dimensionless quantity. And if you were to plot the electric charge, let's call it alpha, the fine structure constant, it would have the property that as a function of energy or 1 over wavelength, smaller and smaller distances or larger and larger energy, then the fine structure constant would increase somehow. Okay. The fine structure constant would increase. It's usual to plot the inverse alpha to the -1, because in various approximations, the inverse is a nice straight line, and it would decrease, the inverse coupling constant would decrease at high energies. That is exactly this phenomena that the point electron surrounds itself with opposite charge, and that opposite charge sort of lowers the charge at large distances, and so forth. All right, there are other coupling constants. The two other important coupling constants are the coupling constants of the Electroweak theory. The alpha here is the coupling constant that's associated with the emission of a photon. That's the electric charge, photon. Alpha. All right, there is the emission, for example, of a W boson. The W boson is governed by another coupling constant, which is the SU2 coupling constant of the Electroweak theory. All right. And if you calculate it using the rules of quantum field theory, number 1, and number 2, incidentally, experimental data tells you what the value of these constants is at low energy, at some value low energy, 10 GeV or some appropriate energy. These constants are determined by experiment. All right. The Electroweak coupling constant is a little bit larger. That means its inverse is a little bit smaller. And it also has a kind of screening phenomena associated with it. And it also varies more or less, the inverse of it also varies more or less linearly. And they happen to cross at a certain point. Now, when I say when they cross, nobody has ever measured physics at such a high energy. These trajectories, not trajectories, these curves are very, very shallow. They vary appreciably only over very, very large scales of energy. The coupling constants only vary logarithmically. They vary very slowly. And so if you were to plot the known Electroweak coupling constant, except follow its renormalization as a function of smaller and smaller distances or higher and higher energies, you would find that they cross. And where do they cross? They cross up at some very high energy, roughly somewheres in the neighborhood of about 10 to the 15th, 10 to the 16th GeV. All right, that's 10 to the 15th or 10 to the 16th times the mass of the proton, way, way, way beyond any experiment that is likely to happen in the next million years, I would say. Well, I don't know. All right, now there's one more coupling constant which is interesting, and it's the coupling constant for emitting a gluon. This is Electroweak. I don't know, that coupling constant, I don't know what to call it. Call it alpha Electroweak. All right, and there's one more coupling constant, and that's the coupling constant for a quark to emit a gluon. That's a much bigger coupling constant, which means its inverse is smaller, but it has the odd property, because of the properties of quantum, with the nonlinear properties of quantum chromodynamics, that the screening phenomena happens in the opposite direction. Instead, roughly speaking, this is a metaphor for the real thing, but roughly speaking, a bit of color, a color charge, creates around it a color charge of the same sign. And that increases its charge at large distances, decreases its charge at small distances. That's called asymptotic freedom. that at small distances, the quantum chromodynamics coupling constant gets smaller, not bigger, has the opposite behavior from electrical forces. And that means that this coupling constant, the inverse coupling constant, increases. Now, we haven't talked very much, maybe we'll get to it a little bit, about unified theories. Unified theories attempt to put into one basic framework all three of these interactions. To think of the photon, the W bosons and Z bosons, and the gluons as belonging to a single family of objects which have a symmetry among them. That symmetry is obviously spontaneously broken, if there is any such symmetry, because otherwise you wouldn't be able to tell a photon from a W or a gluon, so they are different. But one view of it is the symmetry between these things is spontaneously broken, and the spontaneous breaking splits these three coupling constants. All right, so if you follow the strong coupling constant, it also tracks and it crosses the other two someplace. Okay? If you take just the standard model, the unmodified standard model, and you take these three coupling constants, they have a tendency to more or less cross each other at more or less the same point, but I think less is a better description than more. They miss each other by a pretty significant margin, even though the tendency is for them to sort of point in a tempting way to point toward the same value over here. So that leads to the speculation that really there is one primordial coupling constant, spontaneous symmetry breaking, which is the symmetry which relates these three phenomena, is spontaneously broken, causes them to split, but up at some very high energies, perhaps they come together and form a single coherent unified theory. That's the hope. That's an idea. That's a very tempting idea. There is some substance to it. But the problem is, what you'd really like is these three coupling constants to join at a point. You'd like, at some very high energy, these three coupling constants to come together and to tell you that there really is a single phenomena at extremely small distances, which is unadulterated by this spontaneous symmetry breaking. Spontaneous symmetry breaking always has the effect of influencing physics more at low energies than at high energies. That's a common denominator for spontaneous symmetry breaking. It tends to affect physics at low energies more than at high energies. So the hope was that these coupling constants would come together at some point, but they don't. Right? When supersymmetry is added into the brew, then the Feynman diagrams, which define the way that these constants vary, is somewhat modified. What is it modified by? It's modified. Let me show you a kind of Feynman diagram that, among other things, affects the electric charge. The electric charge is, for example, affected by electron-positron loops, like that. Electron-positron loops inside a photon. Here's a photon, here's a photon. This could be a photon exchange between two charged particles. This could be a proton and another proton. The repulsive force between two protons. If you bring the protons very close together, protons are not a good example because protons have a size of their own. So let's take a very small an electron, a pair of electrons. And you look at the force between the electrons. If the distance between the electrons is large enough to allow this kind of loop to be present, then it affects the electric charge, makes it smaller, makes it smaller than it would be if you brought the electrons very close together. When the electrons are very close together, there's no room between them for this kind of virtual loop to take place, and just basically the single Feynman diagram by itself is present. All right. So the source of the variation in these couplings. The variation in the couplings is called running. The couplings are running coupling constants. The source of the variation is Feynman diagrams. When you add super partners into the brew, you generate new Feynman diagrams. For example, the Feynman diagram that I just drew, which has an electron and a positron in it, could be replaced by a similar Feynman diagram in which the superpartner of the electron goes around in the loop. The net upshot is that the way these curves vary is affected by supersymmetry. Now, it's a striking fact that if you were to take every ordinary particle and add to it a superpartner with the same properties except the opposite fermion bosonness of the particle, guess what? Then these three curves cross at a point. And they cross at a point to a very good accuracy of about 1%. Now, when I say they cross at a point, as I said, nobody has ever measured anything up here. What you do is you measure down here, you measure down here, you measure down here. You take the theory, whatever the theory is, you start calculating Feynman diagrams, and you extrapolate. The extrapolation of the coupling constants is to within the accuracy of the calculations to about 1%. The three coupling constants cross at a point. There's no trick in making the two coupling constants cross at a point. Right? That's not a trick. Okay? The fact that that energy is way up high, that's interesting. But to make three coupling constants or three things cross at a point, that either requires luck. In this case, I would say bad luck if it's just luck, because we don't want to be misled by luck. So it either requires an accident of about 1 part in 10 to the 2, or it really represents the addition of more kinds of particles in these loops. And if you actually really just take the supersymmetric partners, add them in, they really do cross to within 1% at a single point. Okay? Yeah.
So do these converge to a point at some energy and then they diverge?
No, it's, well, as I said, nobody's ever measured them, so to say what they do and don't do is a matter of theoretical argument. But the theoretical argument would be that once you get to high enough energy that the effect of the spontaneous symmetry breaking is gone, then it's believed that these would just join into a single coupling constant. Yeah.
The extrapolation you talked about adding the supersymmetry, was that using exact supersymmetry? So the masses?
No, it is not. Right. Okay, all right, let me answer the question the following way. If the superpartners were split, in other words, the superpartners were exceedingly heavy, so heavy that their contribution to these loops would not become important until to very, very high energy, then they would miss each other. You have to assume that the supersymmetric particles are not too heavy for this to be the right picture. How not too heavy? Not too far from the experimental range. Now, this all sounds like a marvelous accident, the sort of things that people cook up to get funding for big accelerators. But in this case, these calculations are quite serious, quite honest, and it really does look like with the superpartners there's a chance. This is called unification, if these coupling constants come together. This is the third, let's call it higher precision. How do you spell precision? Like that? Higher precision unification. All right, so that's the other thing that's at stake. One last point is that if you were also to plot on this the gravitational coupling constant, the gravitational coupling constant gets, how would the gravitational coupling constant look? The gravitational coupling constant, which corresponds to the gravitational force, let's say, between a pair of electrons at low energies, that coupling constant is incredibly small, right? The gravitational force between two electrons at a distance of an atomic diameter, or even a nuclear diameter, or even any reasonable range, that gravitational force is far, far smaller than the electromagnetic force. That means if I plotted the gravitational constant on here, it'll be way up here somewhere at low energy. But the gravitational interactions increase rather rapidly with energy. Do you know why the gravity increases with energy? Right, right. The more energy you have, the more gravity you have. Right? There is no tendency for electromagnetism to do that. If you have more energy, that doesn't mean you have more charge. The charge of the electron this effect here might be considered a little bit of a variation of the charge with energy or distance. But just in an ordinary sense, electric charge is not energy, but gravitational charge is energy. Therefore, the effect of gravity, the analogous effect of gravity on particles would be something which gets stronger with energy, and therefore the inverse of gravity, of the gravitational coupling constant, would fall. And in fact, you can also plot where it would cross these three lines. And it's not terribly far away. Actually, it actually crosses fairly close to this point over here. And so it's another indication of a common scale that might be governing the various forces of physics. A more or less common scale, but these three really do cross, and they're very similar to each other. Gravitational force is a little bit different. You don't quite know how to compare it. You don't quite know how to compare gravity with these three other forces. So to argue one way or another whether it crosses at the same point, that's a little bit dicey. But the three gauge interactions, the three these really are very similar to each other. Yeah.
Is there a fourth, regarding the superpartners, do they fall within these three gauge?
Yeah, they have the same interactions. They have electric charges. So the partner of the electron is called a selectron. S for scalar. S stands for scalar. And it has exactly the same electric charge as the electron, different mass, but same electric charge. The partners of a quark, squarks, so-called squarks, have the same charges as the quark, as the corresponding quark, and also the same color quantum numbers. So squarks interact with the same kind of color forces as quarks, and so forth. Yeah. So no, they do not define new interactions. Yeah.
If the LHC would determine, would discover a superpartner, would that be definitive for supersymmetry?
Oh yeah, yeah. No, I mean the restrictions of supersymmetry are very, very tight. They're very, very tight. They tell you detailed relationships between interaction strengths. Supersymmetry gives you a lot of detail in the particle spectrum and in the particle interactions. And those details would be pretty clear. The only issue is whether the supersymmetric particles, whether their masses are low enough to be detectable at the LHC. If you make them too heavy, this picture doesn't work. All right? But you might be out of luck. It could be that the supersymmetry really is there, and just by bad luck, it happens to set in that the particles are a factor of too heavy to be detected at the LHC. That would be awful. It would mean, we wouldn't know what to say. So, on the other hand, if you make the particles, the superpartners, too heavy, then this control of the divergent self-energies doesn't work very well. And the Higgs particle gets pulled up to higher energy. You need the cancellation. In order to have the cancellation, you must have not too big a discrepancy between the masses of the particles and the superpartners. So if you try to say that the superparticles are there, but they're at 100 times the mass that could be detected at the LHC, a number of these things will just go wrong. The dark matter particles will be at the wrong energy, wrong mass. This higher precision unification won't work out nearly as well. And this control of the divergent self-energy of the Higgs will fail. It won't be as bad as it would be if there were no superpartners, but it will still fail. So if supersymmetry is going to do something good for us in these three domains of experience, in these three domains here, it had better be not too far from the experimentally accessible range. That's what has had, ideas come and go, and they usually don't last very long when they don't do something really good. This idea of supersymmetry has been around for a long time, and it hasn't gone away. That's no proof that it's correct, but it is some evidence that there's something rather attractive and compelling. Compelling, not in the sense that it has to be true, but it has to be tested. It has to be tested. That's what's, yeah.
Is there any connection between more or less standard assumptions about cosmology and the amount of dark matter or the size of the dark matter particles or anything of that sort? Is there any way to relate the two?
Well, I'm not sure exactly what you're asking, but the existence of dark matter has a lot of effects on it.
Cosmological assumptions tell you something about the ratio of helium and hydrogen and stuff like that. It might be they tell you something about dark matter as well.
I'll tell you what the problem is. The problem is, without a more or less specific theory of dark matter, all you really know is the mass density of the dark matter, okay, the mass density of the dark matter. And that mass density per cubic something or other could be 3 or 4 heavy particles or 10 to the 15th very light particles, and you can't tell. Yeah, it could be a Bose condensate of extremely light particles. In fact, that's one theory of it. That's called the axion theory of dark matter. And it could be just a very, very large number per unit volume of very, very light particles. They better be bosons, otherwise you can't squeeze that many of them into a small volume. Or they could be heavier particles. So without some kind of theoretical prejudices, you can't tell what their mass is, and you can't tell very much about them. Other than that they have to be there in order to control the motion of galaxies and so forth, rotation curves of galaxies and so forth. Other than their gravitational effect, we don't have a completely compelling set of arguments about their properties. Nevertheless, with some assumptions, fairly somewhat robust assumptions, the class of theories falls into 2 interesting possibilities. One is particles of a mass of about a TeV, and the other is extremely light particles that form a Bose condensate. And both of them can work. Both ideas seem feasible. And furthermore, anything in between will also work, but there's no theory of stuff in between.
I was just thinking in the beginning, maybe there were only superparticles, and then they all kind of decayed into...
Well, you'd have to have some reason to believe that. I don't know what the very beginning was, but there was a point in time when the universe was a lot hotter than it is. In fact, in which the thermal energy scales were, let's say, way up here somewheres. In that situation, it would be thermal equilibrium which would dictate how many of each kind of particles there would be. And more or less, you would find proximate equality between the various kinds of particles. In fact, just about all the particles would pretty much have the same abundance. Bosons, fermions, more or less all about the same. And so at some time in the past, particles and antiparticles, bosons and fermions, all more or less equally abundant, and pretty much determined by the thermal equilibrium that takes place. If there were too many ordinary particles and not enough superparticles, then the collisions of ordinary particles would produce superparticles. If it produced too many superparticles so that the abundance favored superparticles, then collisions between superparticles would create ordinary particles. And thermal equilibrium, there would be some kind of balance between them. So the expectation was, I don't know what was going on at the very, very beginning, but if we trace back as far as we can, it looks more like there was an equal abundance of these various kinds of things. Yeah.
So, the LSP, which ordinary particle would that be the partner of? Because it would have to be non-interacting, right?
Yeah, very likely a neutral, almost certainly a neutral particle. Why? Well, for one reason is that it's a charged particle is likely to be or a colored particle is likely to be somewhat heavier than its neutral, than a neutral version of it. Why? Because of electrostatic or color forces, color energy densities. So the expectation would be that it would be a neutral particle, but in various versions of the theory, it could be different things. Could be the partner of the photon, it could be the partner of the Higgs boson, it could be the partner of the graviton, which is called the gravitino, and various different possibilities. I don't think there's any definitive idea of what the lightest superpartner is.
What's the difference between the Higgs divergence and the vacuum energy divergence?
Yeah, well, it is different. It is different. The vacuum energy divergence is just the energy of empty space. And in terms of Feynman diagrams, it's just diagrams or virtual particles which sort of populate empty space. Complicated Feynman diagrams, all sorts of Feynman diagrams can take place, but they're in otherwise completely empty space, and they contribute energy to the vacuum. The self-energy of a particle, in particular the Higgs particle, is a class of diagrams in which the presence of basically you can say it this way, the presence of the Higgs particle or any other particle provides a kind of impurity in the vacuum. That's what a particle is. It's an impurity in the vacuum. The impurity has an effect on these vacuum diagrams. Its presence modifies them in a way which is not too different than the plates of the Casimir effect. But you can summarize it by saying the important Feynman diagrams for renormalizing or shifting the mass of a particle are just diagrams which are connected to that particle, like that. So the Feynman diagrams which are sensitive to the presence of the Higgs particle give a mass to, or shift the mass of the Higgs particle, and it is in a sense the same kind of phenomena, except it is, what shall we say, modified by the presence of the Higgs particle itself, and therefore shifts the mass of the Higgs particle, whereas the vacuum diagrams are just shifting the mass or the energy density of the empty space. There's one thing, there's an interesting fact, which we haven't explored cosmology, at least for a number of quarters, but there is one feature of this vacuum energy which is what distinguishes it and makes it rather special. Let's talk first about ordinary energy stored in the form of particles. Lots of particles. They could be dark matter particles. They could be any kind of particles. Eventually, at some point, as the universe expands, these particles separate enough that they're not in violent interaction with each other. They're just more or less sitting there. And as the universe expands, they separate. And as they separate, the energy density decreases. Okay? The energy density decreases because the volume of space increases, the number of particles doesn't increase, and the result is that the energy density of the vacuum, or the energy density of space due to ordinary particles decreases as the universe expands. It works differently for photons than for particles with mass. The reason is the following. The particles with mass, due to the expansion of the universe, eventually come to rest relative to each other. No, they don't come to rest relative to each other. They just participate in the overall expansion. But think of them as roughly being at rest in a local frame over here. Their energy is just mc squared. Or their mass is just their mass. And the way you find the energy density or the mass in a certain region is just to add up all the particles and give each one a mass m. Okay? That's the way you would calculate the energy of just ordinary particles. You just take all the particles in a certain volume and then divide it by that volume. That's the energy density. And then as the volume expands, the particles just move out with the expanding volume. They just participate in the expansion. And the energy density decreases, but the total amount of energy in a volume like this stays fixed. Okay? All right, another example would be a volume of space with photons in it. Photons in it. You can think qualitatively of just having a cavity with photons in it. Of course, in reality, the photons pass out through the walls of this region freely. There are no real walls. But for every photon that passes out, there's also likely to be another one coming in. So you can imagine a region of space, an expanding region of space, where the number of photons stays fixed. But each photon, each wave in here gets stretched by the expansion. Its wavelength gets stretched. And so as its wavelength gets stretched, the corresponding energy of each photon decreases. So that means relative to the massive particles, this is called just non-relativistic massive particles, the energy density stored in radiation will decrease faster as the universe expands than the energy density stored in ordinary particles. This is why today the energy density in radiation, black-body radiation, is vastly smaller than the energy density in protons, nuclei, and electrons, and so forth, because the expansion has stretched the photons, but it hasn't changed the mass of the particles here. If you go back into the past, at one point, the energy densities are about the same. Okay, wait, yeah, go ahead.
I'm trying to figure out exactly how to ask the question, but basically, when you look at a particle as having a wave function associated with it, then how can it be considered a particle and not a wave?
Let's not try to get into the subtleties of quantum mechanics, and let's just say that we're talking about more or less classical radiation in this region. When classical radiation is stretched, the energy density decreases in a certain way. Okay, now, what about vacuum energy? Vacuum energy is just the energy of empty space. Okay? It has the property that as the universe expands, the vacuum energy density simply doesn't change. It just stays there. It stays at the same energy density. It doesn't dilute as the universe expands. All right? So it's just empty space. How could it dilute? Empty space is empty space. Well, that's a caricature of an argument. But the point is, that is the special property of vacuum energy, that it doesn't dilute as the universe expands. Now, it may be that at some time in the early universe, and it is true, that in the early universe, the vacuum energy density was much, much smaller than the energy density in radiation or in particles. It was much, much smaller, and it was not very important. But as the universe expanded, the ordinary sources of energy diluted, but this and this diluted. This, being radiation, became smaller than this, being ordinary non-relativistic particles, but the vacuum energy did not dilute. And that means that at some point, the vacuum energy density will become more important, larger, than either of these two sources of energy. Well, that has already happened. It's already happened that the energy density of the vacuum energy density is about 3 times larger than, it's about 70% of the energy density of the universe today. So at some time in the past, maybe, I don't know, roughly 8 billion years ago, I'm not sure exactly when it was, you have to do a little calculation, 6 billion years ago, there was a crossover where the other forms of energy earlier on were more important, the density was larger, they controlled the behavior of the universe, and then as it expanded, this diluted and diluted until about some X number of billion years ago, the vacuum energy became more important, and today it's more important by about a factor of 3 or 4 or something like that. 70%, how much, so 30% versus 70%, 70% being vacuum energy. How did we get into this? Well, we were talking about the various Feynman diagrams for vacuum energy and the Higgs phenomenon. All right, we got off on a tangent. Any other questions about supersymmetry? About anything? Yeah.
Is there a constant net energy density as we go through that process of increasing the energy density of the vacuum and all the others?
Okay, I think you're asking me about the role of energy conservation in cosmology. Okay. The answer is a bizarre answer. The answer is energy is exactly conserved and it's always exactly equal to 0. There are various forms of energy. One of the forms, there are this form of energy, that form of energy, vacuum energy, but there's also another kind of energy, and it's kind of the kinetic energy of expansion. It's just an energy that's associated with the expansion of space. The energy density associated with the expansion of space, according to the general theory of relativity, happens to be negative. It happens to be, if we define the radius, let's say the radius of the universe at any given time, call it A, it's called the scale factor. There's an energy density stored just in the fact that the universe is expanding. It's a kind of kinetic energy. A dot means the time derivative of A, and it's a kind of kinetic energy. It's proportional to the square of the expansion velocity, and it happens to be negative. That's one source of energy. And then there are all the other terms in the energy. This, that, something called curvature energy, and they all have to add up to 0. That's the rule of general relativity. General relativity insists that the total energy of a cosmological universe should all add up to 0. All right? So the answer is that all the other forms of energy may or may not decrease. If there was no vacuum energy, then these energy densities would decrease, but it would be compensated for by a negative increase in, there's actually some A dot over A squared, some whatever. So energy conservation in general relativity is very peculiar. It's not simple conservation. Or if you try to force it to be simple conservation, then the answer is the energy is always 0, being compensated for by some kinetic energy of expansion. Yeah.
The sum of the energies must be 0, or it turns out that it's 0 because...
No, it must be 0. It's a consistency condition of, it's one of the equations of motion of general relativity.
It's
not a coincidence that the universe being right at the boundary between open and closed.
Oh, no, that's a different issue. That's a different issue. Whether it be open, closed, or on the boundary between them, there are various forms of energy, including, I see, okay, yeah, your question is, all right, so what are the forms? Do we really want to do this now? I'm happy to do it, but, okay, all right. All right. Yeah. This is Einstein's time component of the Einstein equations. All right, what does it say? On the left-hand side is geometry, and there are two terms associated with the geometry of space-time. One involves the time derivative of the expansion factor. This is just, if you like, just think about it as the radius of an expanding universe. A dot over A squared. Why it's A dot over A squared, that's not of any particular significance. You can multiply the whole equation by any power of A you like. It's traditionally expressed in terms of this quantity here. That's one term on the left-hand side. Let me just remind you, the Einstein equations are of the form something geometric equals something that has to do with what you ordinarily call energy and momentum. Energy, or mass, or whatever you want to call it, on the right-hand side. This is not meant to be taken literally. It's just on the left-hand side you have something that involves the geometry of space. On the right-hand side you have sources, and those sources are of the form the energy momentum tensor on the right-hand side. All right, translated into equations, one of the equations has the form of something involving A dot over A squared. There's another term involving the geometry. It depends on whether the universe is open, closed, or flat. Open, closed, or flat. And it has the form of minus, well, depending on open or closed, it's either plus or minus or 0 to flat. And it's something involving 1 over A squared. That's the left-hand side. It depends on the rate of expansion of the geometry, and it depends on the nature of space, whether it be positively curved or negatively curved or flat. So that's what's on the left-hand side. On the right-hand side is the energy density, the ordinary energy density, and we just call that rho. The ordinary energy density means it contains particles, non-relativistic particles, usually called matter. It contains radiation. And it contains vacuum energy. And the matter energy is ordinary matter and dark matter. All right, that's the form of the cosmological equations of motion. But another way of writing them is just to put all of this on one side of the equation. This is the magic of the equal sign equals 0. Put everything on one, put everything on one side of the equation. And then it reads that something is equal to 0. What is that something? That something is actually the total Hamiltonian of general relativity. It's the energy in the sense of the canonical Hamiltonian, the strict definition of energy from Noether's theorem, from the theorems connecting symmetries and conserved quantities. So yes, there's a conserved quantity. We can call it energy, but it contains this expansion stuff. It contains stuff about the curvature of space, and the whole thing has to add up to 0. That's the rules. That's the rules of the game. Other than that, there is no notion of energy conservation in cosmology. No other notion of energy conservation. So, following a volume of space, this part of the energy can either decrease, increase, whatever it does. It'll be compensated for by this side over here. Yeah.
Going back.
We're not getting to supersymmetry, but that's okay.
I want to ask something.
Grassmann numbers, okay.
Yes. Do they show up in Lagrangians of the theory?
Yes. Well, they show up in two ways. First of all, fermion field. Boson fields, they're values, the values that they take on in ordinary, the boson fields are ordinary numbers. Okay? The electric and magnetic fields are ordinary numbers. Fermion fields are Grassmann numbers. They anti-commute among themselves. Okay? So first of all, they show up in the Lagrangian in the form of the fermion fields, but they show up in another way, which is what I was going to get to today. We may decide to postpone it till the next time, since it looks like it's getting late. But the other way they show up is either really deep or very trivial. And I think it's hard to say which. I think it's very deep. It appears that in a supersymmetric theory that there are additional dimensions of space. Now those additional dimensions of space, we have time, x naught, and we have x1, 2, 3. And those are the ordinary dimensions of space, and that's all there is. But in supersymmetric theories, there are additional directions of space, not space-time, but space, and those other directions are Grassmann variables, theta. How many of them are there? We'll get to that. Basically, two complex, or four real Grassmann variables. We can call them theta alpha, two, and think of them as complex, but complex simply means two real, four of them altogether. And it is as if supersymmetric theories are theories which, if you like, live in a space-time which is composed of both ordinary coordinates and Grassmann coordinates. Now this is extremely odd, very, very abstract, but at least one thing you can say. The Grassmann coordinates are small. They don't correspond to big extended directions of space. You can't move around in those. And why do I say they're small? They're small because theta squared is equal to 0. Okay? So like any really, really small number, its square can be taken to be 0. So Grassmann coordinates are small, but nevertheless, they are important to the structure of the theory. And then the way a supersymmetric theory is set up is by defining a Lagrange density, and we'll talk about this a little bit. I was going to go into this a little bit tonight, but it's getting a little too late. But it's a Lagrange density which, first of all, before we get to the Lagrange density, let's talk about fields. Fields ordinarily are functions of the x's. Let's call them phi of x. That's normally the way we think about fields. But in a supersymmetric theory, the fields are functions of x and the thetas. So it's as if, indeed, there were additional dimensions of space, and fields can depend on both the x's and the thetas. Now, the theta dependence is very limited. Why is it limited? Imagine expanding. Let's suppose that this phi was an ordinary number as opposed to a Grassmann number. Then you would write that this ordinary number, phi of x and theta, let's make this a capital phi. It's called a superfield. It's called a superfield because but it's called a superfield, and it depends on position, ordinary position in space and time, and these Grassmann variables. All right, now, you can take any function of Grassmann variables and expand it in powers of the Grassmann variables. Let's suppose, for example, there are 4 distinct thetas. This is correct for an ordinary supersymmetric theory. We'll understand why, but not right now. There are 4 thetas, theta 1, theta 2, theta 3, and theta 4. They can be combined into 2 complex thetas, but let's just take them as 4 thetas. Then phi of x and theta can be expanded. Phi, let's call it little phi now, phi of x which is independent of theta. It's a power series expansion in the thetas. Plus, let's call it theta alpha psi alpha. Alpha is just some index which labels the various Grassmann numbers in the problem, 4 of them in this case. There are these. Then there might be something proportional to theta alpha, theta beta, times, I don't know, give me a name of another field. Psi z. Z alpha beta. This is also a function of x. This is also a function of x. And so it goes until you get to 4 powers of theta. All 4 thetas had better be different. They also have to be different here because any theta squared is 0. So you can have theta 1 times theta 2, but you can't have theta 1 squared. It's not allowed. And eventually you get to theta 1, theta 2, theta 3, theta 4, times some other thing, I don't know, we need to give it a name, d of x. And then there is no more than that. There is no more than that. Another way of saying it is that the superfield is composed of several ordinary fields. A boson field, phi of x. A fermion field, psi. Why do I say it's a fermion field? Well, because it has to be a Grassmann number. The Grassmann number times Grassmann number is an ordinary number. And then another boson type field. And so it goes. A finite number of them, a finite multiplet of fields associated with different particles. And so you can either think of it as a collection of ordinary fields, or you can group them together and do the bookkeeping by saying there's an additional family of Grassmann coordinates, and the field can be expanded in those Grassmann coordinates. So it's a kind of bookkeeping. Once you have the idea of a superfield, you can then write a Lagrange density, which depends on the x's and the thetas, and it's built up out of these superfields, products of them, functions of them, various kinds of derivatives of them. I won't bother writing down a specific Lagrangian, but it's built out of the superfields. And that Lagrangian, the Lagrangian density, depends on x and theta. And the important question is always, when you have a Lagrangian, what do you do with a Lagrangian? You integrate it to find an action. And then in classical physics, it's either the principle of least action, or you use the Lagrangian in Feynman's path integral formulation of quantum mechanics. The important thing is the action. The action ordinarily is an integral of the Lagrange density over the 4 dimensions of space, but now it also becomes an integration over the various thetas. That is the structure of supersymmetric theories, that everything is exactly as if there were some additional directions of space, and the action of the theory becomes an integral not only over ordinary space, but also over the thetas. Now that raises a question. What the devil do we mean by the integral over Grassmann variables? What do we mean by taking a function of Grassmann variables and integrating it over theta? That's obviously an as yet undefined concept. I think we did define the arithmetic of Grassmann variables. You can add them, you can multiply them, you can do usual arithmetic operations. Don't try dividing by them, that gets a little dicey. But adding and multiplying is an okay thing to do. You can do the differential calculus. The differential calculus is very simple. If you want to differentiate with respect to a theta, you do more or less the obvious thing. If you want to differentiate with respect to theta 1, you just find out where theta 1 appears in here. Here it is, could appear here. and you just differentiating with respect to it just differentiates exactly the way you would ordinarily differentiate. You don't have to worry about higher powers of theta. A given theta can only appear to a linear order and no higher. So the table of derivatives is very, very simple. The derivative of a constant is 0. The derivative of something proportional to theta is just a proportionality factor, and that's it. It's a very simple table of derivatives. The question is, what do we mean by the integral over thetas, Grassmann variables? And I'm going to tell you now, the justification for the rules of integration is that they're useful. That they're useful in various contexts. It's completely abstract. An integral is not in any sense a sum. The integrals over Grassmann variables are analogous to definite integrals. They're not indefinite integrals. They're thought of as definite integrals. So when you integrate over theta here, you're doing a definite integral over the entire theta space. I won't bother writing from minus infinity to infinity because theta is a tiny variable which doesn't vary very much. But it's there's no sense, no analog of a indefinite integral. There's only the analog, yeah.
By saying there's no indefinite integral, are you getting away from saying that the integral is the opposite of a derivative?
Very much you're getting away from that because as it turns out, the integral and the derivative are exactly the same thing. Right. Right.
With the d4x, we're integrating over all of space-time.
Yeah.
So that's also a definite.
It is also a definite integral, yes. 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 So I'm just going to tell you, for the purposes of knowing exactly what's written here, I'm going to tell you what the table of integrals is for Grassmann integration. And then we can start to talk a little bit about supersymmetric theories and how you construct them. How you construct them, but the main point of supersymmetric theories is that whatever they do, they preserve the symmetry between bosons and fermions. They ensure the delicate cancellations. If you construct them properly, they can be complicated, interacting field theories, but they will always preserve in the same way that if you construct ordinary field theories carefully, they will preserve Lorentz invariance. They will preserve rotation invariance. They will preserve the various invariances that you built into the Lagrangian. In the same way, by being careful to at every step preserve the supersymmetry, you can ensure that at the end of the day, that these delicate cancellations of Feynman diagrams and things like that are preserved and don't get ruined by interactions, by all the various complexities in the theory. That's the point of it, okay? So the point of it is to set up a kind of calculus of how to construct supersymmetric theories. That's what we're doing. We're attempting to build a calculus which is analogous to the tensor calculus of relativity, which ensures that at every stage we preserve the invariances under rotation, under Lorentz transformation, and so forth. We're talking now about preserving the invariances under supersymmetry. Okay, so we have to know how to do Grassmann integrals. And I'm not going to spend a lot of time. I'm just going to tell you what the rules are. The rules are mostly justified by their usefulness, but I'll tell you some of the rule is pretty unique. Pretty unique, follows from a small number of assumptions. The first assumption is linearity. Let's just talk about the integral over one coordinate. Supposing there's only one Grassmann coordinate, and I want to consider an integral of some function of theta, d theta. All right, the first rule is linearity. Linearity says that if you have A and B can be ordinary numbers. A times, let's call it f of theta, d theta, sorry, A f of theta plus B g of theta, d theta. Very simply, the answer, and a's are just ordinary numbers for our purposes now. That's just equal to a times the integral of f of theta d theta plus b times the integral of g of theta d theta. That's simple enough, just the usual linear rules of calculus. And the only other rule that you really need is that the integral, all right, let's go back to ordinary functions for a minute. What is the integral with respect to an ordinary coordinate, let's call it the dx, of the derivative of a function with respect to x? Let's make an assumption. Let's assume that the function f, integral, definite integral from minus infinity to infinity, and let's add one assumption that the functions that will be interesting to us are ones which go to 0 very, very far away. For most purposes in space-time, we're interested in concentrated regions of energy and momentum and so forth. So for most purposes, we're interested in functions which are vanish far away, large x, large positive and negative x. So what is such an integral? 0. Right. It's just the rule for integration by parts, if you like, so that the integral of a derivative, the definite integral over all space, is equal to 0. That's a rather important formula. It recurs over and over again. We use it left and right all over the place. Let's ensure that it's correct for Grassmann functions. Derivative d by d theta of f of theta is equal to 0. D theta, sorry, d theta equals 0. That pretty much determines the table of integrals. For example, supposing we take for f of theta some constant, let f of theta equal any, let it just be theta. Let it just be theta. Let f of theta be equal to theta. Then what's df by d theta? 1. Just differentiating f of theta with respect to theta just gives 1. So it follows that the integral of 1, which is just 1, d theta is equal to 0. So the definite integral of theta over all theta, whatever that means, is by definition now equal to 0. Okay? The next thing in the integral, the next thing we could have is f of theta could be proportional to, the next integral that we could study is the integral, let's put it over here, integral theta d theta. Okay. What about theta squared d theta? Theta squared is 0, so we don't have to worry about theta squared d theta. Theta cubed d theta, this is the only other thing we have to worry about. What is the integral of theta d theta? Okay. This is not a Grassmann number because it's got two Grassmann numbers. A d theta is counted as a Grassmann number. This is an ordinary number. In fact, you need a rule here. The rule doesn't matter. It's a convention. It's a convention, but it's a convention that this is equal to 1. And that's it. That's the whole table of integrals of functions of one Grassmann variable. All right, so now we can write the integral d theta of any function of theta, and any function of theta can be written as some a plus b theta, and that's all there is, nothing beyond that, The integral of theta times a, well, the integral of theta is equal to 0. So that gives you 0. And the integral of theta d theta, that's 1. I should put the d theta over here. The integral of theta d theta is 1 by assumption. And so the answer is just b. Interesting, yeah.
Is there an f of theta such that the f d theta equals theta?
No. No, because it would have to be theta squared, right? Yeah, but there is no theta squared, right? So we can't, if there was such a function, we would immediately conclude this has to be 0, right? This is part of the story that you can't divide by a theta, but all right, so here's an example. The integral d theta of a function of theta is the last term in the expansion. In this case, it's the term in the expansion with 1 theta. That's the integral of b. Notice it's the same as the derivative. It's the same as the derivative. But that's the integral of a 1 theta of an arbitrary function of theta. An arbitrary function of theta has 2 terms, and it's just the coefficient of the last term. That's the definition of the integral d theta. It's pretty simple. It's amazing that it has any use. What if there were 2 thetas? Let's suppose there are 2 thetas. Well, I'll tell you what the rules are. You can work them out by the same kind of argument, exactly the same argument. In fact, you can repeat the argument pretty much exactly the way it is. But if we had 2 thetas, or a complex theta, which has a real and imaginary part, let's do it that way. A theta and a theta bar. Theta bar means the complex conjugate. You can also think of it as theta 1 and theta 2. It doesn't matter. The general function of theta and theta bar consists of several terms. It consists of an a, which is independent of theta. It consists of, let's call it theta bar psi, where psi is a Grassmann number. Let's suppose a is not a Grassmann number and f is not a Grassmann number. And then there's another term, which is some psi bar times theta. In other words, things linear in the 2 thetas. And then the last term is, I don't know what to call it, b. Theta bar theta, the quadratic term. If there are only 2 thetas, then there's nothing beyond the quadratic term. Theta squared is equal to 0. Theta bar squared is equal to 0. Theta bar theta is not equal to 0. But theta bar times theta is equal to 0. So that's it. That's the most general function of 2 Grassmann variables. As I said, you could write it in terms of theta 1 and theta 2. It doesn't matter. There are altogether 4 terms. Okay, the integral. Here's the table of integrals. The integral d theta bar, definite integral over both thetas, that's equal to 0. Just like the integral d theta is equal to 0. The integral of theta d theta bar. Care to guess what that is? 0. Why? Because it contains an integral theta d theta. Just forget this for a moment and concentrate on the first factor here, theta d theta. That's also equal to 0. Likewise, the integral theta bar d theta bar, that's also equal to 0. The only non-zero integral is the integral theta bar theta d theta bar d theta. Do I have it right? Let me see. I think it's d theta bar. Remember, when you switch signs, when you switch orders, things, yeah. All right, you look at this and you say, look, first of all, I see the integral theta d theta. That was 1. All right, so we do that integral first and we call that 1. And then we're left with the integral theta bar d theta bar. By analogous reasoning, it's also 1. So this is equal to 1. That's the whole table of integrals of integrals of arbitrary functions of 2 thetas. All right, now supposing we integrate function of theta and theta bar. In other words, we integrate not this, but just some general function, f of theta and theta bar.
I think the reason you gave on the linear terms
Yeah.
was backwards. I think that theta d theta will give you 1. It's the d theta bar which gives you integrating 1 will give you 0.
Integrating 1 gives you 0, yeah.
Right.
Yeah.
So that's the reason why that will be 0, because it's integrating 1 with
remember,
the other variable. Theta d theta bar. The d theta bar is the part that
Next to bottom.
Yes, yes, yes. Did I say it backward? I think I might have said it. Yeah, I think you're right. I think I did say it backward. Right. Yes. You're right. Okay. All right. So what's the upshot of an integral like this with f being of this form? Well, the only term that contributes is the term with a theta bar theta here. Everything else gives 0. So the answer is just B. The integral of a function of Grassmann variables is always the coefficient of the last term. That's it. That's the whole theory of Grassmann integration. You simply find the coefficient of the last term in the expansion, and that's the integral. It sounds very, very trivial. It really does sound trivial, and yet its power is enormous. So we'll do some examples. Yeah?
I've forgotten that if we interchange theta bar and theta,
It changes sign.
it changes sign, but doesn't, that's the only.
Yeah, so you have to be careful about the integrals. For example, theta bar theta times d theta bar d theta is equal to -1. Why do I say that? Because if we interchanged these, d theta bar, then of course I would say it was +1. And now we look at it, and in the sandwich here, between the theta bar and the d theta bar, we see something which we've already said was equal to 1. We pull that out, and then we have the theta bar, d theta bar, that's equal to 1. So you have to be careful. Look, this whole subject of supersymmetry divided physics into 2 groups of people. There were those who were able to follow it and those who weren't able to follow it. The ones who were not able to follow it were probably the most distinguished physicists in the world, Richard Feynman, Sidney Coleman. I would include myself among that camp, but not because I was distinguished, just because I was unable to follow it. And the people who were able to follow it were people who were good at keeping track of signs. I go berserk trying to keep track of the signs in supersymmetry, and I have no intuition for it. Not an intuition. I have no. It's just pure torture. It's a form of torture. Okay, never mind. Yeah. So here's the rules. We build supersymmetric Lagrangians out of superfields according to some rules. I haven't told you the rules yet, but according to some rules which preserve the supersymmetry, we need a concept of derivatives and so forth, which is a useful concept of derivatives for doing these things. And then we integrate the action over x and over theta. But integrating over theta always means just pulling out the last term in the expansion of L, which seems totally trivial, and yet it has this enormous power to be able to control and keep exact relationships between particle masses, exact relationships between coupling constants, and the avoidance of all of these divergent quantities which occur. All right, I think I had intended to go through a couple of real examples of constructing supersymmetric theories and show you how they work, starting with the very simplest in just one-dimensional space, or one-dimensional time, but I think I'll save that for next time. And as I said, the subject is very, very abstract, and the abstraction is not what bothered people like myself. It was the simultaneous abstractness of it, and also the concreteness of needing to keep track of signs. That was just too much. Anyway, by now I've learned the subject pretty well, but it took about 30 years. No. What's that? Yes. We celebrate Memorial Day by having a sad lecture. When is Memorial Day? Well, yeah. We will continue on until the end. I will not be away anymore. The boss of the program says I can't go away, so I will be here. I don't know. I have to. We'll find out before then. Does anybody know when the last day of class is? Yeah, this is lecture 6, so we have 4 more lectures.
The last day of class is when you say you won't be here.
Right. Yeah. But the boss has told me that I have to announce it in advance, right?
Did the Grassmann numbers come prior to the idea of their use or were they developed concurrently?
Wait, say it again.
The Grassmann numbers, were they developed concurrently with the development of this physics, or were they?
No, they preceded. Yeah, I believe they're 19th century. I think Grassmann was a 19th century mathematician. They have a lot to do with differential forms. Is what? Okay, June 7th. Right. Well, yeah, that's right. And it will be the last day because I will not be here on June 12th. Okay. Okay, is everybody following the supersymmetry and very happy with all of this abstraction? Okay. As long as you are, I am.
For more, please visit us at stanford.edu.